Distributed Systems from Scratch. This is episode 21, Open Research Problems. 20 episodes taught you what the field knows. This one is a map of what it doesn't. 9 unsolved problems, each one a potential thesis, and at least one that this series has been quietly preparing you to attack. 20 episodes of solved problems. Consensus, solved by Pexos and Raft. Replication, solved by leader-based and leaderless protocols. Partitioning, solved by consistent hashing. Fault tolerance, solved by retrees, circuit breakers, and chaos engineering. But those were the known challenges. This episode is about the unknown ones, the questions driving active research and PhD thesis right now. The frontier. Open problem 1, Programmable consistency. From episode 5, we know consistency is a spectrum, linearizable at the top, eventual at the bottom. Today, you pick one consistency model per database. Spanner gives you linearizable. Cassandra gives you eventual. CockroachDB gives you serializable. But what if different operations in the same system need different consistency? A bank transfer needs linearizable. A page view counter can be eventual. A social feed needs causal. Today you'd use three different databases. That's wasteful and complex. The vision, a single system where you specify consistency requirements per operation and the system automatically selects the cheapest protocol that satisfies them. Systems like COPS, Peleus, and ANA have explored this space, but no production system nails it at scale. This is a PhD worthy problem. Open problem 2, verified implementations. From episode 19, TLA Plus verifies your design, not your code. You can have a perfectly correct TLA Plus peak and a buggy Raft implementation. A buffer overflow in your log replication code won't show up in the model checker. Closing this gap from verified design to verified code is one of the hardest problems in systems research. Ironfleet verified a complete Pexos implementation in Daphne. Verdi verified Raft in Coq. Grove verified a concurrent key value store. These are remarkable achievements, but they're all academic prototypes. None approach production performance or ecosystem integration. The research question: can we build verified distributed systems that are also fast enough for production? Can verification tools integrate with mainstream languages like Go and Rust? Open problem 3, consensus for heterogeneous networks. Raft and Pexos assume a flat network. All nodes are equally far apart. In reality, some links are zero point 0.5 milliseconds, same rack, and others are 200 milliseconds, cross-continent. A single Raft group spanning Virginia and Singapore treats every round trip the same way, even though the costs are wildly different. Ideally, consensus protocols would be topology aware. Place leaders near the traffic. Route Pexos messages along the fastest paths. Adapt when network conditions change. A Paxos attempted leaderless consensus for geo distribution. W. Paxos explored wide area partitioned consensus. Tempo studies topology aware ordering. These are all partial solutions. A general, adaptive, topology aware consensus protocol remains open. Open problem 4, CRDTs for richer data types. From episode 16, CRDTs work beautifully for counters, sets, and text sequences, but real applications need richer structures, spreadsheets, relational databases, 3D models, game state. The challenge is merge semantics. When two users concurrently edit a spreadsheet, one changes a formula in cell A1, the other inserts a row, what should the merge produce? The answer depends on user intent, which is ambiguous. AutoMerge supports JSON like CRDTs. Diamond types handles rich text. Peritext models, formatted text with overlapping annotations. These are all early stage, and the semantic question, what does correct merge even mean for complex data, is fundamentally open. Open problem 5, serverless and disaggregated architectures. Serverless computing, AWS Lambda, Cloudflare Workers disaggregates compute from storage. Functions are stateless, ephemeral, and can scale to zero. But all the distributed systems protocols we've learned assume long-lived processes with local state. Raft needs stable nodes to hold the replicated log. Paxos needs persistent participants. A serverless function lives for milliseconds and then vanishes. How do you do consensus when your nodes are ephemeral? How do you replicate state when there's no persistent process to hold it? Research prototypes like Boki and Beldi are exploring stateful serverless, but we're far from a clean model. Open Problem 6, Distributed Systems for AI Inference. Episode 20 covered distributed training, but inference at scale is its own challenge and it's less well understood. The questions: how do you route inference requests to the right GPU pool? How do you batch requests for throughput while meeting latency SLAs? How do you share a limited GPU cluster across dozens of different models? How do you manage the KV cache for long context transformer models across machines? VLLM introduced paged attention, treating the KV cache like virtual memory pages. Orca introduced iteration level scheduling. Splitwise separates the prefill and decode phases across different machines. These are early, rapidly evolving solutions. The broader question is, what are the fundamental abstractions for AI model serving? We have Raft for consensus, Kafka for logs, LSM trees for storage. What's the equivalent for inference? Open Problem 7, Privacy Preserving Distributed Computation. How do you compute over data that nobody is allowed to see? Three approaches exist: multi-party computation, MPC, lets multiple parties jointly compute a function without revealing their inputs to each other. Fully homomorphic encryption, FHE, computes on encrypted data without decrypting. Trusted execution environments, TE, is like Intel's GX, run computation in hardware isolated enclaves. The problem: all three are 100 to 10,000 times slower than plain text computation. MPC requires massive communication between parties. FHE is computationally brutal. TEES have side channel vulnerabilities. Making privacy preserving computation practical, fast enough for real time distributed applications is a major open problem at the intersection of cryptography and systems. Open Problem 8, Self Adaptive Distributed Systems. Today, humans configure everything. Replication factor set to 3. Hopefully that's right. Number of shards, pick 64. Maybe we'll need 128 later. Timeout value 500 milliseconds. Who knows if that's optimal? The vision: systems that observe their own workload and automatically adapt. Move leaders closer to traffic. Split hot partitions. Adjust replication factor based on observed failure rate. Switch consistency levels based on current load. Research on learned indexes, replacing B trees with neural networks, and auto-tuning databases like AutoTune points in this direction. But a truly self-driving distributed system remains science fiction. Open Problem 9, The Edge Cloud Continuum. The binary distinction between cloud and edge is dissolving. Reality is a spectrum: IoT, sensors, smartphones, CDN edge nodes, regional data centers, hyperscale cloud regions. Each tier has different compute capacity, storage, latency, and reliability. How do you replicate data across this spectrum? A phone is not a server. It sleeps, moves between networks, and has intermittent connectivity. The protocols designed for data center servers don't work. Local First Software from episode 16 tackles the two device case with CRDTs. Cloudflare, Durable Objects, and Fly.io tackle the edge server case. But a unified model for data placement and consistency across the full edge cloud continuum doesn't exist yet. Here's the full map of open problems. and notice how they radiate from the concepts we've covered in the series. Programmable consistency builds on episode 5. Verified implementations build on episode 19. Heterogeneous consensus builds on episode 6 and 7. Rich CRDTs build on episode 16. Serverless challenges the assumptions in episodes 8 and 9. AI inference builds on episode 20. Privacy preserving computation is a new axis. Self adaptive systems connect to episode 10, and the edge cloud continuum connects to episode 17. Every open problem has roots in the fundamentals. That's why the fundamentals matter. How do you identify a research worthy problem? Good science practitioners work around it daily, meaning real pain exists. No existing solution is satisfactory. People are unsatisfied, not uninformed. Theoretical foundations exist, but practical applications lag. There's a gap to bridge. Industry is investing money in the area, and the problem space is growing, not shrinking. Warning signs. The problem is already solved and you just haven't found the paper. You're making an incremental improvement to a mature system. That's engineering, not research. You have a solution looking for a problem. The work is relevant to one specific company, or hardware improvements are about to make the problem disappear. Here is the meta observation about every open problem in distributed systems. They're all some version of the same question. How do we achieve a stronger guarantee without paying the full coordination cost? Stronger consistency without more latency. Better fault tolerance without more redundancy. Richer CRDTs without more metadata. Verified code without slower development. Privacy preserving computation without 10,000 times overhead. The tension between guarantees and coordination cost is the fundamental dynamic of the field. It never resolves. It just moves to new frontiers as old ones are solved. Why are there new research problems? Because the assumptions behind classic papers have changed. Hardware, NVMe SDS, RDMA networking, Smart N ICs, CXL, memory pooling, all invalidate assumptions about I/O latency, network cost, and memory architecture. Algorithms designed for spinning disks and TCP sockets need rethinking. Scale, millions of cores, exabytes of data, billions of users. Algorithms designed for 5 Paxos nodes face entirely different challenges at 50,000 participants. Workloads, ML training, real-time AI inference, collaborative editing, edge IoT. The applications driving system design have fundamentally shifted. Regulations, GDPR, data localization laws, AI governance requirements. Legal constraints are now first-class design parameters, not afterthoughts. If you want to enter this world, here's where the research happens. The top venues: SOSP and OSDI for systems, NSTI for networked systems, Eurosys for the European Community, VLDB and Sigmod for databases, PODC and DISC for distributed computing theory. The top research groups: MIT PDOS, Stanford InfoLab, CMU's Parallel Data Lab, ETH Zurich Systems Group, MPISWS in Kaiserslautern, and UW's Systems Lab. Industry research labs: Google's Systems Teams, Meta's Infrastructure Research, Microsoft Azure Research, AWS's DynamoDB and S3 teams, Databricks and Cloudflare. For each problem area, here's where to start reading. Programmable consistency. Don't settle for eventual. The COPS paper by Lloyd and colleagues, 2011, and Disciplined Inconsistency by Holt and colleagues. Verified systems: Iron Fleet by Hoblitzel and colleagues, and Grove by Chaged and colleagues. AI Serving Orca by you and colleagues, and VLLM Paged Attention by Kwon and colleagues. Rich CRDTs: Shapiro's comprehensive CRDT survey and Klepman's auto-merge work. Serverless: Boki by Jia and Wichel and Cloud Programming, simplified by Hellerstein and colleagues. These papers are your entry points. Follow their references backward and their citations forward. 4 pieces of advice for aspiring researchers. Start building. Implement raft from scratch. Build a key value, store over it. The intuition for distributed systems comes from debugging real concurrency bugs at 3 a.m., not from reading about them. Read papers, not textbooks. Textbooks teach settled knowledge, the things everyone agrees on. Papers teach unsettled knowledge, the disagreements, the open questions, the failed approaches. That's where research lives. Find the pain. Talk to engineers building production distributed systems. Their workarounds, their hacks, their frustrations. Those are your research problems. The best systems. Research solves a real person's real pain. Combine fields. The most impactful papers combine distributed systems with ML, or verification, or security, or new hardware. If you understand two fields well enough to connect them, you're ahead of people who know one field deeply. Let's recap. 1. The core frontier includes programmable consistency, verified implementations, and topology aware consensus. 2. The hottest applied areas are AI inference serving, privacy preserving computation, and self adaptive systems. 3. Every open problem is a variation of the fundamental question: how to get stronger guarantees without paying full coordination cost. 4. Changed hardware, scale, workloads, and regulations are creating new research opportunities where the classic assumptions no longer hold. 5. The best research comes from combining distributed systems with another field: ML, verification, security, or new hardware. Cross pollination wins. Next and final episode: how to read papers and find a PhD advisor. The practical guide to entering the research world. How to read a systems paper efficiently. How to find an advisor who matches your interest. How to write a research proposal. And how to decide whether a PhD is right for you. The series finale. That's episode 21. The open research problems in distributed systems. The map of what we don't know yet. One episode left. The series finale. Thanks for watching.